behalf of the project leader of this work, Professor Natalia. He unfortunately couldn't come here, but I will try to do my best to present our joint results. So we will talk about interactions between aerosol and urban meteorology. And motivation starts from highlighting importance of aerosols in climate system on a global scale. They are the only factor which somehow compensates the anthropogenic impacts on climate. This is a figure from the recent IPCC report, and we see that aerosols at least somehow compensate other human-induced factors in terms of global warming and effective radiative forcing, which is a key metric of this process. And also we see that the impact grows in time because more and more emissions, more and more aerosols emitted. But recent years this trend stopped in contrast to other emissions. And in urban contexts, aerosols are also especially important, and there are many interactions between urban emissions, urban meteorology, including urban-induced circulations, urban breeze, urban heat island, and so on. And they, of course, affect human health, especially small aerosols like PM2.5. And in this context, there are two important metrics. So when we are focusing on human health, it's important to analyze near-surface aerosol concentrations. And when we are analyzing climate change trends and aerosol contribution to these trends, it's important to analyze prolonged contact, which could be characterized by AOD or aerosol optical density. So in this study, we will analyze urban aerosol and one of factors of climate change in Moscow megacity and its interactions with radiation and urban heat island. And we will use both observations and online integrated modeling, and we will analyze aerosol properties and so on. So a few words about study area. So this is Moscow, and we have some unique observations. We have two sites where we could measure urban IOD. We could measure IOD according to Aeronet standards, and these 2 points allow us to estimate urban component of IOD, so contribution of the city to aerosol optical density. And we also have quite dense network of near-surface environmental measurements, which measure different parameters, including PM10. So we will use these two data sources. And now let's move to modeling. So in this study, we use the model COSMO-ART. It is a online integrated chemical transport model. It is based on the model COSMO, which is developed by international consortium led by Hydrometeorological. And so COSMO part is responsible for meteorology, ART part is responsible for chemistry, and with respect to urban component, in COSMO there is scheme Europ. It's simple bulk parameterization, but our previous studies have already shown that it is quite efficient, that it could nicely capture urban heat island, urban-induced circulation, and so on. But before our work, these schemes have never been used together due to some technical problems in model structure, coupling between these schemes. So this study is up to our knowledge, the first when these models are used simultaneously in online model. And we use this model to model aerosol content in Moscow with different emission scenarios or with 2 kilometer resolution for quite short period in spring. And now some more details about emissions. So it's always a problem to define them with enough detail. And we start this problem with taking CAMS data, which is quite coarse. It's available at 6 kilometer resolution. I mean, CAMS data on emissions. But we need 2 kilometer resolution. And we propose an original approach how to redistribute these values using such predictors as industrial error fraction and road error fraction. And these fractions were taken from well-known OpenStreetMap dataset. So we redistribute emissions in space. We also make some corrections according to make our dataset in agreement with local inventories, which exist for Moscow. And we propose a set of numerical experiments to analyze many factors influencing aerosols and climate, including different levels of emissions. 1x is standard emissions. Also, we try to use threefold emissions and emissions with increased fraction of black carbon. And we also analyze the impact of boundary conditions of the urban scheme, how it interacts with chemical model, and the default aerosol climatology which exists in the model. And firstly, results for long-term observations. So there is the most valuable thing which could be derived from these observations from Moscow is estimate of urban component of aerosol optical depths. And we see it for different spectral, different parts of spectra. In average, the most important from here is that in average overall spectra, urban pollution is responsible for about 20% of the whole IOD. And another interesting result is the total IOD is in Moscow is decreasing because city is becoming more clean, industries are moving away, cars becomes more environmental friendly, and so so we have this trend. And now let's move to modeling. Here we compare for Moscow Observatory site results of our simulations with different emissions. Firstly, for aerosol optical depths, we see that when we have default emissions, we have underestimate our observations. Here, color shades are clear sky conditions and full sky conditions. Especially strong decrease is when we don't have boundary conditions. So here we have only urban emissions, and here urban emissions and background aerosol transfer, aerosol advection. And when we increase emissions, we have something closer to what we observe, and sometimes we bit overestimate. But when we go to near surface concentrations, the situation is a bit opposite. So at 1x emissions, we have only slight underestimation of observations, and with threefold emissions, we have strong overestimation. So from here, we suggest that something goes wrong in aerosol transfer in boundary layer scheme in the model. So this is a thing to be analyzed in next studies. Also, we analyze how our model captures the urban impact on the aerosol optical depths. So this is different. This is model to observation comparison for this delta difference in IOD between two sites for different emission scenarios. And scatter is quite wide. But in general, the model captures the trend, which is quite good. And also, we make model evaluation not for one site, but for many sites. according to network existing in Moscow, and we classify sites according to different zones, different land use, and see that for natural area, 1x simulations with 1x emissions are more or less fine with observations. But when we have stations close to highways, we strongly underestimate observations here. And for 3x emissions, we overestimate observations everywhere. And the model underestimates the intra-city variations of air quality. Because we have 80% range between natural areas and highways according to observations, and only from 70 to 30% difference according to model in different scenarios. We also analyze aerosol impact on radiation and temperature and compare it with the impact of urban canopy scheme. And so here we see effect on direct and diffuse irradiance. Aerosols decrease direct irradiance, increase diffuse irradiance, decrease global irradiance, while urban canopy scheme slightly decrease diffuse irradiance due to decreased urban albedo, which is parameterized in TerraUrb. This is effect on, okay, I will skip this. And this is also interesting effect. This is how aerosols and urban canopy scheme affect temperature. So this is mean aerosol effects. And we see that they are quite weak in comparison to effect of urban canopy, in other words, urban heat island. But it's important that this effect exists in independent without dependence of the impact of net radiation. Because when we have black carbon, we have increase of radiation balance, but still increase of temperature, which is really surprising. Okay, and I will skip this, and these are our conclusions. I will leave it here, and more details could be found in the paper, which is now submitted and hopefully will be published soon. So thank you for your attention. I am not sure that I can answer all questions, but Natalia will be very happy if you contact her. Thank you.
Thank you for the presentation. So any question from audience?
Maybe I'll ask a question then. So this is a very interesting piece of work. How do you see how it can be used? Because we have a lot of models, right? We don't only have COSMO-ART, but we also have WRF, CHEM, as we have seen before. So do you think there's an opportunity for us to exchange these notes on how to bring all these models into the right direction towards better representing these feedbacks?
Yeah, actually, I think that it demonstrates the importance of model intercomparison studies because we have many models, many schemes, and in some model we have one effect, in other model we have another effect, and observations are often not sufficient to evaluate these models, but at least model comparison could give more understanding about such effects.
Yeah. Thank you very much. Good
Thank
point.
you.